Hello. Did you start your sixth chapter tutorial? Say I'm done with sixth chapter. Next Tuesday, move into seventh chapter. I get the feeling that it's pretty easy now. Course has become very easy. Piece of cake. Isn't it? No. Attend classes. That's the magic word. Everything becomes easy just like that. If you come and park, everything just becomes easy by itself. Get into the habit of parking. Park where you are supposed to park your car. Whatever it takes. Put a candy in your mouth. Put a chewing gum in your mouth. Park where you are supposed to park. It's pretty easy. Maintain continuity. It's easy. Discontinue. Back again to square one, you're going to start again. Over and over and over and over. So you complicate your own business for no reason. So since you want strategies, these are my strategies of how to go through a course. First, learn to park. Next, learn to maintain a continuity. If you can do that, I think everything else will take it by itself. If you cannot do these two basic things, very basic things, then you are going to struggle throughout your 4 years in all the course. No doubt about that part. Any other questions for strategies? I'm more than happy to answer. You know what's the riddle of the strategy question? Even to ask a strategy question, you have to park where you're supposed to park. So there you go. That asking that question itself solves the problem. You cannot catch me in CP or in the mess or somewhere in the corridor and ask me the question. So if your mind even is thinking of asking this question, I think that itself we have solved your problem. So it's that easy a course, but is made so complicated into one big drama. There's nothing anybody can do about it. I even looked at your 6th chapter problems. I'm thinking which problem is tough there. I'm not even able to come up with it. It's like there's nothing there. Left hand side, right hand side. So even today if I want to do problems, I got nothing for you. It's like you will just answer verbally how to solve the problem. It's that easy. You can actually make it more complicated by putting more streams, more appliances. So before I do problems, let me ask simple questions. A recap. I have water at some temperature and P1. Somehow, everybody saw the video and all that, right? Somehow, I increase the pressure of the water. What gadget or appliance did I use? 2 marks. I will say I used a rocket. Who is with me? To increase the pressure of water, I used rocket. No? I used satellite. No? What appliance did I use? Louder? Huh? Okay, onion layers. Let's peel the onion now. So I said there's water at 100 degrees and P1. I increase the pressure of water. So question again, listen how funny this question is. So did I increase the pressure of water? Huh? Louder? Okay, yes. What appliance did I use? What appliance did I use to increase the pressure? Louder. What appliance? I thought last class I mentioned there's only 4 appliances in this course. What are the 4 appliances? Not nozzle. So if you are saying some great words, what are you thinking? What am I using to increase the pressure? Louder. I hope you know little bit of, I hope you are keeping track of the English language. Compressor is compressing and increasing pressure or it's expanding? Huh? Compressor is compressing or compressing is expanding? Louder. Oh, compressor is compressing. So when you compress, pressure is increasing or pressure is decreasing? So after 2.5 months, I'm still peeling the onion layers. Yeah. Okay. So which device now will I use to increase the pressure of water from P1 to P2? Now that's a course right there. What's going on? Pick up the game. Yeah? Otherwise this is how I have to do it. Because I cannot go further without knowing whether you understand or not. So if you say, compressor, compressor, and I have no idea. I think the answer also is weak. Compressor. It's like all disconnected sentence, like words. The ink will trail off. If you bark at me like loudly, compressor, don't you get it? It's obvious. Then I'll be like, great. And now you increase the temperature of that compressed water from T1 to T2. What appliance did I use? Okay. Huh? Pressure cooker. So apples didn't go with apples. Apples went with, let me complicate it and put some vegetable market. So you're basically talking about the entire market. I asked about a isolated process and you put a market at me. You heard your friend behind say something. Louder. Heater. Now if you put all this together, now he is hesitant. Now he got cut. He thinks now I fooled him. I didn't fool anybody. I'm not in the business of fooling anybody. I'm in the business of only fooling myself. That's all, if you didn't know. If you put everything together, okay. Engineers are very simple-minded people. They write English with very simple languages. Compressor, heater. I wonder now, let's switch the question differently. What does the device which is called as condenser do? I want to see whether you understand the simplicity of an engineer's mind. Okay. I wish you just even said it condenser. Okay. I'm just seeing how much you will stay away from the title that's given to that appliance and try to reinvent one new definition for it. When the engineer has broken his head and said, we are all dumb people, we'll keep it very simple and we'll write condenser. So blender, I wonder what a blender does. Blend. Okay. The condenser will condense. So now, will it try to pull the heat out or will it try to give the heat? Okay, good. So the state change will happen from gas to liquid or liquid to gas. So your major appliances are heated. What is the opposite of heated? Condenser. And then you have compressor. So usually when you compress, is the system doing the work? Is that air that is doing the work or somebody is doing the work on that air or water? Huh? Work is being done on the material. So once it is all ready and fired up with high pressure and temperature, obviously that material wants to do work. Typically what kind of work we are talking about in this course? Turbine work. It goes to a turbine and it rotates the shaft. So turbine is the material doing work on the surroundings or the surroundings doing work on the material. After all this, you again freeze up. Okay, so I have to go back to compressor. Is compressor doing work on the material or the material doing work? Is turbine material doing work on the surroundings or surroundings doing work on the material? Excuse me. Your material is all compressed and heated up and it's ready to do work. I'm answering my own question, if you didn't notice. It's ready to do work. Now the material is doing work on the surroundings or it's being done, work is being done on itself. Okay. Who's still tripping on this? Who's really still tripping? Take a cold material. First you compress it. What happens when you compress the spring? What happens? Huh? It comes closer. Then what happens? Then what happens? If you compress something like a spring, what happens? No, honestly, have you compressed anything? If you pull a catapult, what happens? It simply will freeze out. Huh? Yeah, work is being done, that's fine. What is it, what will it do if you let it? The spring will smack you where it has to smack you. Yeah? So is it ready to do work? So to get something to do work, what should you do from its equilibrium state? You put work on it, you compress it, there is no free lunch. If you want something out of anything, you first have to input something there. I hope you don't play catapult without doing this. I don't know how you will just from here fire away. I'm not sure which catapult you're talking about, but good luck with it. That is the work of the compressor, get it? First you have to put it under stress and press it so that it will explode back on your face. And then you can use that to do some useful work. Before you hit a tennis ball, you have to take a look backwards and only then hit it front. If you have to go forward, you have to push back. Only then you can go forward. I wonder how the rowers do it. Rowers push like this, forward. Huh? Oh, they push back, but they go forward. Hey, that's pretty good. You have to push back to push forward. Get it? So you take whatever material that is sitting quietly, you put it under stress. How do you put it under stress? There's two ways commonly you can put something under stress. Leave out the chemical stress. Either it is P or T. You're still thinking, what else is it? Jesus. Either you compress it or heat it. It will get stressed out. Then what it wants to do? Explode. Don't worry, it will explode. That is what work is. Work is against a resistance. I thought I went through this long time ago. If there is no resistance, there is no work. Vacuum is not work. There is no expansion on anything in which there is no resistance. Only if I lean on you, you want to disprove me. So that is why I will lean on you. And then you will do work for your sake. That's why leaning is required. Get it? Without that leaning, there is nothing that you will push against. You will not do work. How many of you still think that you will freely do work against nothing after this course? Like you will wake up one day and you will just simply do work. How many of you are still in that mindset? You need something to be put on you so that you get stressed, and then you want to fight against that stress and you will do the work. And good luck. So what are the two ways you will stress? You have to compress and you have to heat. What will you get out of it? You will get expansion work. You will get a push. You will get a thrust. And then you can use it for whatever. You want to move a turbine, you want to push something, you want to hit a tennis ball. So how does the tennis ball machine work, where the ball comes firing out? There must be something that's compressing at the back. Get it? That is why you hear that sound. There's a release of that spring. And then the ball comes up. Go and think of some examples, lots of work examples. Without compression, there is no forward work. And then what happens? After you do work, are you still energetic or you slowly begin to tire off? I would like to hear this story. It gets more interesting now. Would you get, as you keep doing more work, do you tire off or you start to feel more energetic? Sure? Sure? Okay. Personal experience? Okay, wonderful. So now that heated high pressure spring or material is now done work, so it begins to get tired. So what happens to its pressure? Further increases or begins to ease off and decrease? Begins to ease off and decrease. What happens to that heat that was used for expansion and pushing? Does it continue to get heated or does it cool off? Cool off. So when your pressure decreases and when your temperature decreases, did your balanced internal energy further increase or did it come down and you are tongue out exhausted? Exhaust, no? Okay. Okay, now you can shoot off questions. Who is still tripping on this? This is also chapter 7. There's only 4 appliances. You take any material, you compress it, and then you heat it, it's ready to do work. After it does work, it cools off. So you take water, You compress it and then you heat it. What could water become most probably? Louder? Huh? Vapor. And then that vapor will explode and do the work. And it cools off and the pressure goes down. What could the vapor again become? It could become a mix. But then again you want complete water to start again. Because that remaining vapor you will use it for some side application. So eventually it's back again to, but you want to completely make it water properly. What appliance will you use? Condenser. Back again compressor. Back again heater. Back again work turbine. Back again condenser. Can you write the loop now? Can you write the loop? Write it. It's for you to write only. First time in the class, right? Write it. Take any material, write the cycle. You can write about yourself itself. I wake up, I get pressed, then I get pushed, and then I do work, and then my pressure is down. I cool off, then I cool off some more in the refrigerator, and then I come back and the cycle happens again. I wake up, I get pressed, I get pushed. Write your story only. Why do you want to write poor water stories? Write your story. Start with the material, first you compress it. So learn to write the cycle. Put boxes, that's enough. Compressor, COMP. So here what should I put? Work is being done on the material or is the material doing work? So how should my arrow be? Inside pointing or outside pointing? Huh? And what should I write here? W dot. So if I ask you here, there is a P1, there is a T1. Can you fill this part? What? P1? Huh? As soon as I say, huh, the student will back off. Check. I just said, huh, just for fun's sake. Sure? And? So should I write P2 is greater than P1? Okay. Next, take it into another box. Heater. Endothermic or exothermic? Endo. So the arrow should point inwards or outwards? And what should I write? Now what do I have here? P2, T1. What should I write here? And then what should I write? T2 greater than T1. Next, you're ready now to do work. Another box. Turbine. Now you're doing work on the material or is the material doing work on the surroundings? On the surroundings. So inward arrow or outward arrow? What should I put? W dot. So now what happened to your P and T? Should I write P3 T3 or P2 T2? Obviously P3 T3. You did work. Got it? Yes? You did work. So then what should I write? P3 is less than P2. T3 is mostly less than T2. You did work. You cooled off. You cooled off. You expanded. Next, you want to bring water back again. Another box. What is this box? Condenses. I have to remove heat or I have to put heat? Inward arrow or outward arrow? Outward arrow. What should I write? Q dot. So here you have P3, T3. What should I write here? P4 I should write? P3, T4. And now you are back again. That's a cycle. Get your arrows right, okay? Two places work, two places heat. Why do you have to look at it? Why you look at it? Look at your book. Look at your book and write. Two places work, two places heat. Which are the work appliances? Turbine and compressors. Which are the heat appliances? Heater and condenser. That's all. Any questions? This is chapter 7-2. You've already started chapter. There's an overlap between 6 and 7. So is the mass rate continuously flowing? Yes? Okay. Can the velocities change at different times at different inlets and outlets? Okay. Can the positions of the Z, can it change? Potential energies, can it change? Yes. Obviously enthalpies will change based on your temperature changes and pressure change. Internal energy will change. Can you separate how much heat you removed, how much work you did separately? Can you quantify it and write it? Okay. Many of you are saying yes. So then at the compressor, if I want you to just separate only W dot that is going in, what will you do? Have I given you sufficient data here? Have I given you sufficient data? Sure? How will you tell me what is the work that's gone into the compressor? Yeah, it's isothermal, that's fine. But I didn't say assume ideal gas. Huh? What will you do? How will you isolate and find only the amount of work that is being done? How will you isolate and tell me just how much work is being done in the compressor stage? CPDT will give you DH. Wonderful, that's a good start. CPDT will give you exactly DH between this state and that state. Then what will you do with it? One second, then what will you do with it? That you tell me and I think you are on the right track. I've given you P1, T1, then P2, T1 is given. I want you to just isolate and tell me how much work has gone into the compressor. So your friend says, let's do CPDT. But if you do CPDT, where is DT? There is no DT here. What you will do? Tell me what you are going to do now. Huh? PdV, where is V? But I have not told you how it changes. So you will do P1 plus P2 by 2. How you will find work done? That you tell me, I will go to the next appliance and ask you a question. How will you isolate and tell me how much work has gone into the system in the compressor? How do I find it? You cannot make a guesswork, you have to look at the diagram. Correct. So I know some internal energy at the beginning or enthalpy at the beginning. You should not use internal energy. We are talking about work, or we are talking about, so what should you think of? Enthalpy. So how will I be able to find enthalpy for the inlet? From where? Excellent. Will I be able to find enthalpy for the outlet? From where? Table. Then what will I do? Excellent. That's it. Where does this come from? From your balance equation, from your global equation. Yes? Yes. Will H2 be greater than H1 or H2 will be less than H1? H2 will be greater than H1 or H1 will be greater? Sure? Sure? Then what will be the sign convention, not the sign convention, what will be the answer of your W dot? Will it be plus or will it be minus? Input is on this side, output is on this side. So Q is on the right side of your equation or on the left side of your equation? Q is on the right side. W is on the right side or on the left side? Huh? Go look into your equation. Q is on the right side or left side? Look into your equation, man. Right side. All the inputs are on the right side. All the outputs are on the left side. Don't trip on this. Got it? All the inputs. So endothermic is heat coming in. Inlet is something that is coming in. All that is grouped and put on one side. On the other side is work that is being done on the material and one that is going to the exit. That's the output. Got it? Sorry, I said it the other way. Work being done by the material on the outside to the surroundings. And that and going outside is grouped on the left side. You receive heat and you do work. I think your tutors must have told you receiving heat sign convention is plus, receiving work sign convention is minus. Giving heat is minus, giving work is plus. Can you write it one more time? They flip-flop, the heat and work. Receiving heat is plus, receiving work is minus, giving heat is minus, giving work is plus. So receiving heat is like the money that you receive. Work is like the spending that you do. So your balance will always be Q minus W. Yes? Your bank balance. How much you received minus how much you spent. Work is spending, Q is receiving. That's why the sign conventions are flipped. So now all the inputs are grouped on the right side, all the outputs are grouped on the left side. Correct? So Q is on the right side and W is on the left side. So now we are assuming there is no heat transfer here, so Q became 0. So what did you tell? You told me that easily I can find changes in enthalpy and I can tell you how much work is being done by the surroundings on the system. This is a compressor we are talking about. So H1 is on the right side or H1 is on the left side? The inlet. H1 is on the right side. H2 is on the left side. So you said what? The sign convention, the work is being done by the surroundings on the system. Should it be positive or negative? Negative. Then H1 should be greater than H2 or H1 should be less than H2? Yes. You cannot go wrong with this. Obviously you cannot. Got it? You cannot go wrong. You have to get a minus because work is being done by the surroundings on the system. So how do you do this? You have to go to the tables for the P1 T1 and P2 T1. You have to pull the H's out, not the U's out. You have to pull the enthalpies out. And you have to do a DH and you can tell how much is Q dot. But DH itself does not have a time there. You have to multiply that by M dot to get your W dot. Otherwise you will not get W dot. Okay, now go to the second one. How do I get Q dot independently for the heater? You know P2 T1, you know P2 T3. Sorry, P2 T1, P2 T2. Now can I do CPDT? Pretty easy. You can do either DH, go to the table and find the DH, or you, for that material, you assume a CP, ask for a CP value, and then you do CPDT. And again you should write, so the best way to do is, in the exam, for the heat, you in the parentheses after you write your final answer, underline it and you write endothermic. Exothermic, if you're that much worried, should I put plus, should I write minus, how should I leave it? For the work, what you write is, in the parenthesis, system on surroundings, surroundings on system. Obviously, whoever is marking knows that you know really well. And you don't have to worry about whether you should put a plus or a minus. Get it? You have made your point by saying endothermic and exothermic. Yes? For the work also you write, don't be lazy, you write system on surroundings, surroundings on system in your final answer. So can we isolate like this and do it for each step? Can we also combine everything? For all this entire thing, can you put everything in your equation? Or do you have to write multiple equations? No. For the entire this loop, do you have to write, if I ask what is the overall, what kind of question can I ask here? What kind of question can be asked here? Other than independent work done, independent heat removed, independent heat supplied, independent work taken. If you combine everything, what kind of question can be asked? Total heat, total work. Can I not give the mass flow rate and ask you to find the mass flow rate? Is that a question? I'll give you the loop. Will it work? No? So the common question that usually is asked is at the end of this, what is your enthalpy? Here, at the out, when it comes out of the condenser. Or everything is given including the out. So basically what is out is what goes in. So they will ask what is happening here. What is the enthalpy of the material after it goes through this entire process? Can you do that? It's a summation. Do one stream question. I'll give you a stream question. Write the picture. Quickly write the picture. Help me number. Where should I number? Obviously pictures suffice. You should know where's the inlet, where's the outlet. Where should I number? Shall I put 1 here? Where should I put 2? Here. There is one more stream coming in. Should I number it here? Should I number it? Yes, 3. Then the mix, should I number it? 4. Is my numbering correct? Okay. I'll put 1 arrow here so that you know, and 1 arrow here. This is a cooler. So what should I put? This is a cooler. This box is a cooler. What should I put? Huh? No. Any arrows should I put? It's a cooler. So something like this, what should I put? Okay. So it's a cooler. I have T1, I have T2. Will T2 be greater than T1 or less than T1? Okay. Now there is a stream that is coming at T3. That's why I've labeled it as T3. So this is 35 degrees. This is 5 degrees, T2. So some heat has been removed. This T3 is 25 degrees. What is T4? Will it be between 25 and 5 or will it be above 25 or less than 5? So this is 35, it gets cooled to 5, then it gets mixed with the 25. So will it be between 5 and 25 or will it be greater than 25 or less than 5? So you cannot go wrong with your answer. So can I independently find how much Q dot is pulled out? Yes. All I need is table. H1, you give me the numbers correctly, then I will understand. H1 and go with the numbers. What should I get from the table? H1 and H2. Then I get the DH. Then I get my Q. Great. Now that H2 is coming and it has M2, correct? M2. And then there is M3 coming in. Am I telling the numbers correctly? M dot 3. What would be the mass equation when M dot 2 meets M dot 3? Yeah, it's the same material. How does it matter whether it's same? But M dot 3 is a different stream. It's coming at a different temperature. No, I'm not talking about energy. I'm just talking about the mass equation. Now M dot 2 is coming from here, M dot 3 is coming from here, and then I wrote a number 4. So do I need to write a mass conservation equation? What would that be? M dot 2 plus M dot 3 is equal to M dot 4. Very good, that's your continuity equation. What would be the corresponding energy balance equation? M dot H2 plus M dot 3 H3 is equal to M dot 4 H4. Now can you find T4? Yeah? Can you find T4? Can you find T4? How will you find T4? You write that equation. You write m dot 2 plus m dot 3 is equal to m dot 4. Write it quickly. And write the energy balance equation. M dot 2 H2 plus m dot 3 H3 is equal to m dot 4 H4. The question is, final question is, what is T4? Any other additional data that needs to be given? I think everything is given, right? Find T4. Find H4 and that is one way. That is one way. But for that I need to give you CP. No, if you simply find H4, okay, you can do that. You can find H4 and how would you do it without going to the table? Without seeing the table from the two equations. So nothing. At the m dot 4 H4 you write it again as m dot 2 plus m dot 3. And all the H4s are like T4. You are assuming the DH to be infinitesimally small. Got it? So wherever you have enthalpies, you can represent it in terms of temperatures. I think I'll get to that in chapter 7. So you don't, it's like you consider infinitesimal DH. So H4s can be written as T4s. H3 is T3. H2 is T2, H1 is T2. CPs all get cancelled out because CPs are same. It's the same material. It's the same material. So you just have to do a little bit of manipulation, arithmetic, and you can find T4. Any questions? Did you get to this question in the tutorial? Somebody said yes. 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 So did you go to H4 and look in the table and then come back and see T4? Why not? You could have done it. It will still work. You can find H4 and go to the table and come back and see T4. You might have to do some interpolation. Yeah, I'll just start chapter 7. Any questions? You're welcome to come later. Catch you guys. I think your marks might be given